Now we have the potential formulation, but yet we do not have a direct relation between the potential and the charge density. That is what we need. Now for that we are combining the two laws. One is our Gauss's law in differential form, that is del dot E is equal to rho by epsilon 0. Also our potential formulation, that is E is equal to minus del V. That is, instead of this E we can substitute from here, that becomes del dot of minus del V. So del dot minus del V, we write it as minus del square V. Now I will explain what is this del square is. So you first see that we are taking the del dot of del V. So del V is the gradient of a scalar function called the potential, and we are taking the divergence of that, that is del dot del V, or we call it as the del square V. So the del square V is equal to the RHS. So minus sign can be taken to there, that is minus rho by epsilon 0, that is del dot del V, or del square V is equal, that is del dot V is equal to del dot of minus del V, which is equal to minus del square V is equal to rho by epsilon 0, or simply del square V is equal to minus rho by epsilon 0. So we connected them, that is, here in the LHS we have the potential, the scalar potential, and the RHS we have the distribution or the charge distribution, rho is there. So based on this we can connect them, the V and the rho are connected now. Now what is this del square? Now we know that del dot means, so what is this del V? Del V means the gradient of a scalar. So let us write that, let V be our scalar function. Then what is del V? We know that del V is equal to x cap into dou V by dou x. This is what we are writing from the definition of the gradient. So x cap into dou V by dou x plus y cap into dou V by dou y plus z cap into dou V by dou z. So now we have del V. Now what we are doing in the next step is del dot of this, that is, now this is a vector function. So we can take the divergence of a vector function, no problem. So let us take that, that is del dot. So del, let me write the del at first. So del is equal to x cap into dou V by dou x, sorry, not dou V by dou x, dou V x, just write del only, that is x cap into dou by dou x plus y cap into dou by dou y plus z cap into dou by dou z. Now take the dot, that is del dot del V. Now this is a vector quantity and this is a vector quantity, so we can operate this del on that del V. So x cap dot x cap is equal to 1 and dou by dou x of V. That means we get, so the first time I will write, that is dou by dou x of dou V by dou x, or which is equal to dou square V by dou x square. So we got a second order partial derivative. So we can here we get, that is dou V by dou x. So together we can write it as del square V is equal to dou square V by dou x square plus dou square V by dou y square plus dou square V by dou z square. Now I can take the V outside, then what it remains is that dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Now this together, okay, into V. So the term in the square bracket, that is a dou square by dou x square plus dou square by dou y square plus dou square by dou z square, which is called the Laplacian. So instead of writing all the second order derivatives, we can write it as del square. So del square means that is nothing but the combination of two differential operators, that is, we know the divergent and the gradient. We applying it directly or together to a scalar function and we get it as del square V. So del square V means the second order. So it actually reads as, it is the dou square V by dou x square plus dou square V by dou y square plus dou square V by dou z square is equal to something like this. So this is the is equal to minus rho by epsilon 0. This is called the Poisson's equation. So now we got a second order partial differential equation. Actually we have written here a partial differential equation in 3 variable, and it is a second order equation. So if we could able to solve this equation, that is del square V is equal to rho minus rho by epsilon 0, and we can calculate what this V is. So from that we can calculate what exactly E is. But you know that it is always tedious to solve differential equations, especially partial differential equations of second order kinds are not always exactly solvable also. So it is quite tedious work to do with. So we will find another way to connect in between. We will invert this V is equal to something like that. So we will do that later, but it has its own application when you learn more about electrostatics in some advanced techniques. When you learn, we will get into that. So that is it is a useful thing actually. But for simpler configurations like 1 or 2 charges, or a charge on a line, or a surface charge, or many things, we do not need to solve this one. We can use some other techniques for that, and we can reduce this equation to another equation that is called the Laplace's equation. So now for a charge, this is a region for there is a charge. If there is a charge density rho, this is the equation, and there are places where there is no charge but there can be field. So in such cases, for a charge free region, the right side becomes 0 and del square V is equal to 0. That is called the Laplace's equation. We can solve this also to get the value of V, but for simple cases like point charges and distribution, simple distribution that we learned previously, we do not need to solve this tedious equation. We can find simple equations, something like what we done for electric field or something like that. So we can find simple equations for them. So we are not going into this. This is actually the advanced part of electrostatics. So we are not going into that, just getting just making familiar you to that, this only. So let's go to the next session, that is the potential due to a point charge. Actually, what is the potential at a distance r from the distance? Imagine that we have a charge q. Okay, so here we are going to find a similar equation, that of, we know the equation for electric field due to a point charge, E is equal to 1 by 4 pi epsilon 0 q by r square. So it's a direct equation. We can connect electric field with a charge. So similarly, we are going to find an equation for potential from the charge here, charge and based on its distance or something. So this is q, and we want to find the potential at a point P, that is r distance away. Okay. Now let us see, we know that, let's imagine q itself be at the origin. Now what we have to calculate, V of r is equal to, that is we have to calculate the potential. Like equation for the potential is simply minus integral E dot dl from the first reference point to the point at which we want to calculate. Now we want to calculate at the point r. So reference, we conveniently choose infinity as the reference. We can choose any reference point, no problem, but infinity is conveniently chosen. Now we have to evaluate it. So let's evaluate for a single charge. Now we know that what is the value for a single charge, that is you have E here. Now at a distance r from a charge, at this point what is the value of electric field? We know that E is equal to 1 by 4 pi epsilon 0 q by r square into r cap. So that is the direction for 1 by 4 pi epsilon 0 q by r square into r cap is the value of electric field. So we got E. Now what is the dl? So we can deal it in spherical coordinates. So dl is equal to dr r cap plus r d theta theta cap plus r sin theta d phi phi cap. So just take the dot product between them and then integrate. So we are taking the dot product, only these two terms exist, that is all the other terms will be cancelled, that is 1 by 4 pi epsilon 0 q by r square into dr, that is q by 4 pi epsilon 0 1 by r square dr. Now the integral is from infinity to r, the minus sign is from the definition of potential. So now we know that it is very easy to solve. 1 by r square become minus 1 by r, and for the minus 1 by r, if you give the minus sign, so minus sign will go away and we get its value, that is q by r within the limit infinity to r. So, when you give the upper limit, it becomes q by r minus q by infinity. Q by infinity means that is actually 1 by infinity, which is 0. So, finally, we get the same result as q by r. That is the advantage of taking the reference point as infinity. We only remains with this. So, we got the expression for the potential due to a single point charge, that is V of r is equal to 1 by 4 pi epsilon 0 q by r. Now, what if there are multiple charges? Let us see. So, if there are multiple charges q1, q2, q3 etc., and they all make a distance r1, r2, r3 etc. Now, already we said that the potential has the property of superposition. That means, if you have multiple potentials, you can just simply add them, not a vector addition. So, V2, V3 etc. So, the first one will make a potential at the point, that is 1 by 4 pi epsilon 0 q1 by r1, then the second will be q2 by r2, and the third will be q3 by r3. So, if there is another one, q4 by r4. So, just take the sum and we get the value. So, in summation notation, we can write it as 1 by 4 pi epsilon 0 summation over I is equal to 1 to n qi by ri. And here note that the potential is, so potential is depend only on the 1 by r. There is no 1 by r square relation. The 1 by r square dependence is for electric field, and for potential it is simply 1 by r. That means potential do not fall as fast as that of electric field. So, V of r is equal to 1 by 4 pi epsilon 0 qi by ri. Now, this we got. Now, from this expression we can find the expression for a continuous charge distribution. Imagine that this is a continuous charge distribution and we want to find the potential due to this at a particular point. So, what we do? So, for that we consider a small elemental volume of that. So, we considered a volume, let that volume be some d tau. So, we have a d tau volume inside, this volume is, let it be d tau, and this d tau will consist of a charge. If the charge density is rho, then the charge inside is rho d tau. So, what becomes? So, rho d tau, we got it. So, the potential due to this elemental volume is, we can write it as V is equal to, let me write it as dV, because it is a very small potential due to the very small charge, is equal to 1 by 4 pi epsilon 0 rho d tau by that r square. Now, to find the total potential, what we have to do, just take the total volume integral, that is integral dV. So, integral rho d tau by not r square, it is actually r, because it is the potential. So, rho d tau by r integral rho d tau by r, that is V of r is equal to 1 by 4 pi epsilon 0 integral rho d tau by r. So, this is the expression for finding the potential due to any finite charge distribution. So, we can find, using this we can find the potential due to any charge distribution, and using that, when after arriving at the expression for potential, we can simply calculate, simply take a derivative of that or the gradient of that to get the final, that is you can use the E is equal to minus del V relation to find the final electric field. So, now this is written for a volume charge distribution. Now, individually for a surface charge distribution, this expression becomes, now here the charge is distributed over a volume. Now, what if it is distributed over a surface? Then it becomes V of r is equal to 1 by 4 pi epsilon 0 integral, here rho d tau is the charge. Now, when the charges are distributed over a surface, that becomes, the elemental charge becomes sigma dA, that is sigma dA, that is simply the dq by r, and if the charges are distributed along a line, this becomes V of r is equal to 1 by 4 pi epsilon 0 integral lambda dl by r. So, these three equations are enough to calculate the potential due to finite charge distribution. So, let us do one example of that. So, for that, so this can actually done, we are going to find the potential due to a disk of charge, and which has a charge density sigma, okay. And we want to find, and its radius is capital R, and we want to find at a distance z above its center. So, symmetrically above its center there is a point, let this point be some p, we want to calculate the field at the point p, okay, due to this surface charge distribution. So, for that what we do is that we have to consider an elemental part of that. We are going to consider a small circular strip, a strip of area from that and which has a radius smaller. Now, this strip consists of some charge. Okay. What is the charge inside that? That means the charge dq is equal to what is the area of the strip into the surface charge density. What is the area? Let us see. This strip will has a diameter or the radius r, that means it has a circumference of 2 pi r into, let us imagine this has a width, okay, and let me draw it one more. So, I am just enlarging it. So, this is r and let this be dr. So, this will have an area 2 pi r dr, that is the area times sigma. So, 2 pi r dr sigma is the charge inside it. Now, what is the potential due to this at this point? So, usually when we calculate the potential or the electric field, when we calculate the electric field, what we do usually we have to consider a strip from here, and due to this strip there is an electric field in this direction, there will be an electric field in this direction, due to this part there will be one along, that means it will make a shape of a cone. Then we have to find the vector sum. Actually there are a number of steps are there, but in calculating the potential there is nothing like that, because this will make a potential there obviously and this will make a potential there, this will be, that is each part of this strip will contribute to a potential at this point, but they are all scalar quantities with a positive sign. So, we can just simply add them, that is each part of this strip will contribute some potential there. So, we can just add them. So, when we add them we get that, what we get, this is the total charge. So, V is equal to 1 by 4 pi epsilon 0, just ignore this. So, let me write it then later we see. So, V is equal to, let us see, V is equal to, V due to this strip is equal to 1 by 4 pi epsilon 0. So, what is this? So, from each portion of this strip the distance to this point, okay, that is this is here, this is what we are considering, this circle, and from any part of that circumference or from that strip there is a distance to this point, that is what we need, that is rho by or sigma dA divided by r is there, that r is that 1 by r is the distance from the charge to the field point or where the to the point where we want to calculate the field. Now, this is r, small r, and this is z. Then what is this distance? This will be z square plus r square under root, that is root of z square plus r square. So, now the charge is 2 pi r dr into sigma divided by, we get it as root of z square plus r square. Now, this is the potential due to that strip. Now, we want to find the total potential due to the entire region. So, to finding the entire region, you can see you can take another strip from here, another strip from here. So, we can make it into concentric circular strips and each of them will contribute to the potential. So, to make it you have to take a smaller circular strip here, that means the radius is something around 0 and 2 radius is the maximum, that is the capital R. That means simply we have to integrate it from 0 to r. So, the expression will be, so this is exact expression, that is you have to integrate it from 0 to r, V is equal to 1 by 4 pi epsilon 0, 0 to r, 2 pi r dr. So, there is a sigma missing. So, here we have a sigma 2. So, just wait. So, there is a sigma. So, 2 pi r dr sigma divided by root of r square plus z square. So, you have to integrate it to get the final answer. So, how can we integrate it? So, simply, so what cancels? 2 and 2 get cancelled and pi get cancelled. Finally, it becomes sigma by 2 epsilon 0 integral r divided by r square plus z square dr. That is what we got. So, now we want to calculate this integral. For the calculation of this integral, we can use the method of substitution, that is, let us take u square is equal to r square plus z square, and what you get is that z is a constant because we are going to calculate at a particular point above the disk. That means this is a fixed distance. So, when you take 2u du is equal to the right in the RHS z square is a constant, so it vanishes. So, what happens? What remaining will be is equal to 2r dr. So, r dr is equal to u du. So, what it becomes? This is equal to sigma by 2 epsilon 0 integral r dr becomes u du divided by, instead of root of r square plus z square, we can put u square there. So, root of u square becomes u. So, u and u got cancelled. So, that is u. So, this is the integral and u get cancelled, and finally, we get integral du. Integral du is simply u, that is sigma by 2 epsilon 0 into u. So, what is actually our u? U means u square is root of r square plus z square. So, u is equal to root of r square plus z square. So, we can substitute it here. So, instead of u, we can substitute root of r square plus z square from the limit 0 to r. So, this is the limit. Now, what would be the value? Sigma by 2 epsilon 0 will be in common and put the value r, that means root of capital R square plus z square minus, what is the lower limit? When you put the lower limit, it becomes 0 square plus z square, that means root of z square, that is z. So, finally, we get a value sigma by 2 epsilon 0 into root of capital R square plus z square minus z. So, let me write the final answer. Yes, here you have the answer. So, this is the final answer. So, that is V is equal to sigma by 2 epsilon 0 root of r square plus z square minus z. So, what do you feel any advantages? I do not know. In the next step, you may feel that. That is, this is actually we have done only up to potential. H we did not calculated the electric field, but the advantage is that you do not need to worry about the direction. That is the main thing when main problem while you are dealing with electric fields. You have to consider what is the direction of that main field or the elemental field, then based on that you can integrate. So, there to this point we have not considered anything about the direction of electric field. We get V directly, or very simply we got the potential. Now, to find the final electric field, what we can do is that E is equal to minus del V. Take the del V, that is the gradient of this function, to get the final answer. So, you did not need to bother about anything about the direction, you will get the direction automatically from this equation. That means, the del V itself contains a direction, that is gradient is a vector quantity. So, let us see that this is V is equal to sigma by 2 epsilon 0 root of r square plus z square minus z. Now, if we calculate the minus del V here, for calculating minus del V, we have to actually use the cylindrical coordinate system, but instead of that we are using in the Cartesian, even though it is not a problem, because we have to calculate E is equal to minus del V. We use minus is here, then some z cap into dou by dou z. Since the given function is only a function of z, it is not a function of capital R, because capital R is a constant for a specified disk. There is no small r here also, only z is the variable. So, since z is the only variable, you have to take the derivative or the gradient with respect to z. So, minus z cap into dou by dou z is the only term that exists, and minus dou by dou z of V, that is we can put this V here, that becomes z cap into sigma by 2 epsilon 0 get outside, and dou by dou z of root of r square plus z square minus z. So, we can just take the derivative of that, so which is very simple, and finally we get its field as this. So, this becomes root of r square plus z square, that becomes 1 by 2 root r square plus z square into some 2z from here. So, 2 and 2 get cancelled, and finally the derivative of z is minus 1. So, with a simple differentiation, actually it is actually a very simple differentiation, we reached at the electric field, instead of calculating or instead of bothering about the direction to find E. So, in the previous classes I think we have done some similar problems to find the electric field due to a simple straight line, So, we have to do a lot of time in finding what is the, we have to consider two elements, what is the direction of electric field due to this, what is the direction of this, and you have to take component to add them, then finally we could integrate. But here we do not need to bother about any of this, and we got the potential directly. Directly means you do not need to worry about the direction. That is a very, very powerful thing about the potential, and from that we could able to take a minus del V. So, for taking the minus del V, you do not worry about whatever be the shape of this distribution, what is the direction, there is no need. So, everything is contained within it to get the direction. So, finally we got the answer E is equal to sigma by 2 epsilon 0 z divided by root of r square plus z square minus 1 into z cap. So, this is the advantage of potential formulation. So, we can do it for many similar kind of distributions, and let us sum it up what we have learned during this short course on, I say it is short course because there we have to learn a lot more. We can do a lot more problems on this, and there is something called some advanced techniques on this, that is based on the Laplace's equation and the Poisson's equation we learned before. So, all about this electrostatics are the relation between three quantities. What are the three quantities? One is rho. Rho means actually it represents the charge, means that this is the charge density, and there is something new that is called the electric field. So, electric field actually connected with the force with the Coulomb's law, and finally potential. So, these are the three quantities. For connecting them, actually we used only two things, only two basic laws, and the remaining were only some mathematical tools, that is the vector calculus done all the other things. So, what were the two rules? The first rule is the Coulomb's law, that is the force between two charges is directly proportional to the product and inversely proportional to the square. So, that is the basic law, one of the basic inputs. The second one is the superposition principle. So, using that we found what is the electric field is. From that we found the properties of electric field. We discovered that is it is curl is 0 and it is integral E dot dl over a closed loop is 0. Those were all mathematical formulations, and from that, so that means there is only two physical input, but the remaining else were only the mathematical formulations. So, we got E. So, from that property of E we defined another quantity, a scalar quantity, that's called. Then we connected all of them. Now, we have 6 equations to interchange or interconvert between them. So, if you are provided with the rho, you can go to electric field using this equation, that is 1 by 4 pi epsilon 0 integral r cap by r square into rho d tau. This is actually the expression for electric field. So, if you are given with a rho, you can go to E. Now, if we are provided with an electric field, you can go back to the rho using these two equations. We need two equations for that, that is one is del dot E is equal to rho by epsilon 0. You just calculate the divergence of this will be equal to rho by epsilon 0, and as an additional input you can use del cross E is equal to 0 also. So, using these two equations you go back to from E to rho. Now, there is from E we can move to V, that is the equation was V is equal to minus integral E dot dl, and in reverse we can go using this equation, that is if we have V with us, then we can go back to electric field using E is equal to minus del V. That is what we done in the previous problem. Now, we can connect these two also, that is from V we can go to rho using this equation, that is the Laplace's equation, del square V is equal to minus rho by epsilon 0. That means if you are provided with this V, so you can, if you are provided with the V, you can calculate the del square V, and we get the value of what were the distribution here. So from this we can calculate the charge distribution or the charge density, and we can come from there to here, that is if you are provided with a rho, we can calculate the V also. So in general rule we use it in this way. If you are given with a particular distribution, a rho, okay, that is what we have done in the previous problem. We have a rho, that is a charge distribution. Then using this law, that is V is equal to 1 by 4 pi epsilon 0 integral rho d tau by r, we can find the V, and using that we can find E. Actually there is an equation to calculate directly from, we can move directly from rho to E, that is this equation, but what we have told is that this equation is a vector equation, or it is a vector sum, so it is very difficult to calculate. So instead of that we are going in a longer path, but it is an easier path. That is advantage of this. From rho we comes to V, then we go to E. So this is the whole thing that we learned during the course. We can sum it up in this triangle with a 6 or 7 equation and 3 quantities. So this is the total summary of the course we have conducted. That is, we can interconvert between all these 3 quantities very simply. Now what is the next level of electrostatics? Yes, we can apply each of these laws to different cases, different materials. What happens when you go inside a material? What happens at the boundary of a material? What happens when you put through conductor? What happens inside a conductor? And many things are actually remaining, so we can deal it in another course or something. So that's about all this. So we are concluding here, and thank you.